All right, 8.4, rational applications. We're going to look at a couple type of popular questions where you use rational equations. One involving current, like wind or water current, tailwinds, upstream, downstream. And then some work problems where you have people working separately or people working together on a job. So let's jump right into it. We're going to start off, a couple of the first ones, I'm going to teach you the setup, but it's not actually going to be a rational equation because of the information that's given. But then if they change what's given, then you kind of have to go down this rational equation path. So let's look at number one. It says a boat makes a river trip downstream. That's with the current. So remember, downstream is with the current. And it takes about 3 hours. The return trip upstream takes 7 hours. So this is against the current. And the current of the river they give us is 4 miles per hour. Find the average speed and the length of the trip. So before you get started, the first thing you need to understand is for these equations, there's a formula that distance equals rate times time. And rate is your speed, so another little way to think about this is your speed. So D equals RT. So let's make a little chart. So I'm going to make D and R. T, and we're just going to kind of put a few lines here so we can organize all of our stuff. And let's start putting in the information. So the first thing they said was we were going downstream. So this is downstream, which is with the current, so you're going faster. And this is going to be upstream. So they don't really tell me how far we go, so I'm just going to put, D in here for distance. And we made the same trip both directions, so distance is the same both ways. That's pretty important for this problem. We don't know our speed, so our speed in general, if you're going downstream, it's going to be the boat speed plus the current. And if you're going upstream, it's going to be your boat speed minus the current, because you need to take away, you're going to be going slower because you're going to subtract the river's current. And the time we do have 3 hours to go downstream and 4 hours to go upstream. So let's kind of label our variables here. D is distance, we already have that one. But B is going to be the average boat speed. And then we're going to let C be the speed of the current, which we know. And T is time, D is distance, so good to go. So what we can do is in our table, we can actually plug in, we know the current. The current was 4. So I'm going to put a 4 in here. And a 4 in there. So now we have our current. So we basically have an equation. We have D equals rate times time. So if I set this up, I have the distance equals B plus 4. That's my rate, times time. And then the other equation, equation number 2, I have the same distance, is B minus 4 times, I don't know why I put a 4 down here. That's a 7. It wasn't 7 hours total. It was 7 hours to come back upstream. So times 7. Well, basically, we have a system of equations, and they're both equal to D. So what I can do is I can do substitution, and I can basically grab this stuff right here and substitute it for D. So this one's a pretty easy type problem because it's just going to be, I only have one variable missing. I'm just missing B. So I should be able to set it up this way. So we're going to have B minus 4 times 7 equals B plus 4 times 3. And we're going to solve it for B. So distribute 7B minus 28, 3B plus 12, minus 3B from both sides. And if I do that, I get rid of my B's over here. But now we need to add this 28 to the other side. And I'm going to get 4B equals 40. So B equals 10. So I know that my boat speed is 10 miles per hour. So what do we need to find? We need to find the average speed of the boat. Got it. 10 miles per hour. And now we need to find the length of the trip. Well, once I find B, I can pretty much just plug it in here. So if B is 10, 10 plus 4, that would be 14 times 3. Well, that'd be 42 miles. And hopefully I get 42 when I go the other way. If I put 10 in here, 10 take away 4, well, that's 6 miles per hour going upstream times 7 hours. That comes out to be 42. So it looks like the length of the trip, 42 plus 42, the length of the trip would be 84 miles. So a pretty long boat ride. So 84 miles each way, and the other part we answered was 10 miles per hour was the average speed. All right, so that type of problem, we set up our chart. Boom, we could just use system of equations. So let's go down to the next one, see what we got. A little bit different information in this one, but I'm going to roll with the same type of setup. I see it's a speed problem. So we're going to do D, we got R, we got T. Get my two columns. This one's not really upstream, downstream, but we have with the tailwind. So with the wind. And coming back, we're going to have against the wind. All right. So with the wind, it says an airplane travels, or it takes an airplane 4 hours to go 1,000 miles with a tailwind. So a couple things we don't know here. It looks like we need to find the speed of the plane and the speed of the wind. So we need, I'm going to let P equal the plane speed, and we'll let W equals our wind speed. And so going with it, we're going to have the plane speed plus the wind speed. So we'll be going really fast. And then it takes 5 hours coming back. So 5 hours on the return trip against the wind. Same distance. But this one's going to be P minus W. So again, I have an equation set up. And, basically I have 1,000 equals P plus W times 4. And then I have 1,000 equals P minus W times 5. And using substitution again, like we kind of did before, you're going to run into a problem, because if you put both of those, set them next to each other, I'll just kind of really fast, I wouldn't write this down. But if you try to put these two and substitute that in for 1,000, you're going to get P minus W times 5, and then you're going to get P plus W equals 4, and you have one equation with two unknowns, so you can't really do that. That's not going to be an option. So you really can't go that route, because you have one equation with two unknowns. So you're going to have to solve this one like a traditional system. We got to actually grind it out and probably use elimination here. So let's clean this up a little bit. I'm going to set it up so it looks a little bit more normal. So when I distribute here, I'm going to have 4P plus 4W equal 1,000. I just kind of like the constant over to the right because it looks more traditional. My next row is going to have 5P minus 5W equals 1,000. And now I got to somehow find a way to eliminate. I got to get opposites there for one of the coefficients. So I'm going to multiply the top row by 5 and the bottom row by 4. If I multiply everything here by 5, everything here by 4, I should be able to eliminate the W's if I do this right. So I'm going to have 20P plus 20W equals 5,000. Remember, the 5's got to go all the way through. Then I'm going to have 20P minus 20W equals 4,000. Now, since I have opposites right here in this row, I'm going to combine the rows. And we'll have 40P equals 9,000. and divide both by 40. Divide by 40, divide by 40. And I'm going to get P equals, and let's kind of crank this out. 9,000 divided by 40. 225. So it looks like I've got the plane speed. The plane speed is 200, not 55. I guess I'll fix it like that. 225 miles per hour is the plane speed. And if I plug that back into an equation somewhere, it doesn't matter which equation it is. I should be able to get the other one. So maybe I'll use this top equation here because it's all nice in addition. So 4 times 225, that's 900. And 900 plus 4W equals 1,000. So 4W equals 100. So it looks like the wind speed was 25 miles an hour. Then you can always go back, and I'm not going to do it for time's sake here, but you could always go back and plug it in the video and make sure that it, or plug it in the chart and make sure that it works. But it's the same thing as doing the equation. All right, well, you might say, well, I can solve all those problems just using a system of equations. So let's look at number 3, because number 3 is a little bit different here. This one's a little bit more challenging. So it says a kayaker travels upstream, downstream. We got the average speed, but we don't know the current. So let's go in here and let's kind of look at this. So I'm going to do my typical distance, rate, time. And I always want to do my up and downstream. So we're going to go upstream first, which means we're going to fight the current. We're going to go against the current. And then downstream coming back, which is nice. We get to kind of chill a little bit. And got 3 and 3. Those are the same. But we don't know. It says the speed of the kayaker is 2 miles per hour. So our speed is going to be 2 plus the, or actually we're going upstream. So this one is 2 minus the current. And this one is 2 plus the current. And we don't know the time. So I'm kind of stuck here. So I'm going to call this is going to be time going up and time coming down. So let me put these in here. So C is the speed of the current. T up is the time going up. T down is the time going down. Probably didn't need to write those out. But if you look at this problem right away, I'm like, oh crap, I have 3 unknowns. I don't know this, I don't know this, and I don't know that. So the big idea here is 3 unknowns. So we're in a bit of a pickle. We can't really set it up and use a system of equations to solve this. So I'm going to do a little bit different maneuver. So if you look at, distance equals rate times time. If I wanted to kind of rearrange that and repackage that a little bit, to get time, all right, to get time, if I divide both sides by r, that'll tell me what time is. Time is p over r. So I could set up a couple equations here, and I could say, well, if I want to find the time up, and I need the time down, I could be able to set up 2 of these different setups. So hold on one second. And I just noticed on our notes, there's one piece of information that we don't have on here. So it'll be added when you guys get it. But the total time of the trip is 4 hours. So that'll hopefully be typed at the top by the time you guys get these notes. But the total time is going to be 4 hours. So I'm going to put on my little chart here, equals 4 hours down here at the bottom. All right. So what I can do is I can set up an equation because it should be true that the time going up plus the time going down has got to equal 4 hours. And I can kind of use this little piece right here to give myself a couple rational expressions. So the time going up is distance divided by rate. So distance divided by rate. So I'm going to have 3 over 2 minus c. And then we're going to add to that the time going down, which is the distance over 2 plus c, has got to equal 4. Well, what we have now is we have one of these rational equations that we need to kind of work out. And what I need to do is I need to find the least common denominator. So I think the LCD for this one that I'm going to use is going to be, and remember this is just kind of a 1 down here, is I'm going to use 2 minus c, 2 plus c. So I'm going to multiply every single piece of this equation by 2 minus c, 2 plus c. So 2 minus c, 2 plus c, and that's going to get multiplied by all of this. And then there'll be some things cancel out. So in the first expression there, the 2 minus c's cancel out. So I'm going to have 6 plus 3c. And I don't really like how that looks. It's kind of smashed in there. So let me just kind of write it out a little bit better. 2 plus c, 2 minus c. And so the 2 minus c's cancel out, and I distribute. And then over here, the 2 plus c's cancel out. So that's going to be 6 minus 3c. And now over here, I got to do 4 times both of those. So 4 times 2 plus c, 2 minus c, because there was nothing to cancel on the bottom. So let's clean up that equation. I'm actually going to move over here where I have a little bit more room. Get rid of our chart. So getting rid of the chart and tightening this up, I have 12 equals 4 times, well, when I multiply that out, that's 4 minus c squared. So that's going to be 12 equals 16 minus 4c squared. And I subtract 16 from both sides. And divide both sides by -4. And I'm going to get c squared equals 1. Take the square root of both sides. And it looks like the current is 1 mile per hour. So pretty slow, chill moving current. So our current is 1 miles per hour. And if we put it back in the table, we should be able to figure things out. Unfortunately, I kind of erased my table in there, but we could plug it back in and it would be fine. We actually could find our time going each way if we really needed to. All right, so I changed the title up here to kind of match what I want in the notes. But so we know that the current's 1 miles per hour. And now what I'd like this to do, I'm going to kind of erase this. And it says, what is the average speed of the current? Which we've got that. It's 1 miles per hour. That was our C. And now let's figure out the time in each direction. So if we go back and I kind of slap our table back in here that we had in the beginning. And so we went up, we went down, we had 3, we had 3, we had the boat, which it said the speed of the kayaker is 2, so we had 2 plus the current, which we now know is 1, 2 minus the current, which we now know is 1, and then we're trying to figure out the time up and the time down, all right? Well, if I set up my equation, I know that distance equals rate times time. So on this first row, I have distance equals the rate times the time. And to find the time, if I divide both of them by 3, it looks like the time up is going to be 1. Actually, upstream should be slower than downstream. Thanks, girl. So upstream is going to be slower, downstream is going to be more. So let me just kind of tweak this a little bit. For the top row, distance equals rate times time, divide, and I get the time up is going to be 3 hours. And just by making them equal 4, once I know that this is 3 hours, this is 1, but I could divide the other way. I could do distance equals rate times time down, divide, and time down is going to be 1 hour. So that's how you can also go back. So you should be able to get all 3 unknowns, the C and then the 2 times, once you get the 1 open. All right, let's switch gears and let's jump into some work problems. And these can be pretty tricky. They look very simple, but they're kind of tricky here. So it says, and I got 2 types. So it says, Andre can paint a room in 6 hours. Jason can paint the same wall. Should be the same room. The same room in 3 hours. How fast could they paint the room if they worked together? So one can do it in 6 hours, one can do it in 3 hours. Together, you would think it should be faster than either of them working on their own. And I'm going to give you kind of a little cheat for this. So for these work problems, you can do basically the time it takes for 2 people. We'll just call them person A and person B. If you, let's put a 1 over that. If you go 1 over the time it takes for A plus B to work together, should be the 2 fractions separate. So these are kind of like rates. You know, it's kind of like, well, you know, if it's per job, you can do 1 job in so many hours. Well, that should be the cumulative or the sum of, you know, one person's rate, 1 job for 6 hours, the other person's 1 job in 3 hours. When you combine those, you should be able to get 1 job in the total hours. So let's kind of set this up. So on this one, I'm going to use the people's names. So we're going to go, you know, 1 over the time that it takes Andre plus 1 over the time that it takes Jason should equal 1 over the time that it takes together, both of those. So I'm just going to put together, or you could put Andre plus Jason, whatever you want. Well, let's fill in some numbers. So we have 1 over 6 hours for Andre plus 1 over 3 hours for Jason is going to be 1 over the total hours for together. It's right there, girl. So now basically I have a rational equation I got to kind of deal with. I got to figure out. So I'm going to do the least common denominator. And looking at the bottom, I have 6, 3, and x. So for the numbers, it's 6. And there's only 1 variable, so it's just x. So I'm going to multiply everybody by a 6x. Everybody. And 6x divided by 6 is just x. 6x divided by 3 is 2x. And 6x divided by x is going to be 6. And pretty easy equation to solve now. It's 3x equals 6. So it looks like 2 hours. 2 hours is what it's going to take those guys to do it together. Now, normally it doesn't come out to be a whole number. Typically it comes out to be some sort of a decimal or a fraction. But that's the setup. The big setup is it's 1 over, so that way it's kind of a rate. It's like 1 job per so many hours, and it'll come out right. So let's try the next one. There's a little different twist to this one. So it says Marie and Ken can clean a house together in 4 hours. So this one's a little bit different because we know the together part. Together in 4 hours. So if I kind of start with my setup, it's like, 1 over the time it takes Maria to do it, plus 1 over the time it takes Kim to do it, should equal 1 over the time it takes Maria plus Kim. Well, on this one, we actually know the right side denominator. So I don't know, what do I have? It takes Kim 6 hours. So we got Kim. and we got the total, but we don't know this other one here. We don't know TM, which I'm just going to call X to make life a little bit easier. So looking at all those, it looks like my LCD is going to be 12x. So let's multiply everybody by 12x. Which basically gives me 12 plus 2x equals 2x, that's going to be 3x. And subtract an x from both sides. So it looks like it takes 12 hours for Maria to clean the house by herself. She must be pretty slow. So if it takes Maria 12, it takes Kim 6 together. They could bust it out in 4 hours. This really would kind of help if you own a business and you're trying to schedule and you know what people can do separately. You could say, well, what if I slap them two together on the same job? How much faster can we get it done? This would be a nice little way to kind of figure out where you should deploy your manpower or wool manpower. All right, hopefully this helps you out. See you.